So, welcome back. In this lecture, again we continue discussion on Fourier transform. Okay, so the discussion but not on L1 or L2 functions, but a new class of functions. So, first we define this new class of functions. So, this is called Schwartz space, Lorentz Schwartz. Okay, so he introduced this class of functions which are well suited to analyze PDEs in the free space, that is on the whole space Rn. Okay, so all functions are defined on Rn. Okay, so this and integrals are also over Rn. So let me not repeat that. Okay, so this Schwartz space denoted by S. So this is S of Rn. Okay, so this consists of functions. So let me denote by phi, a typical element which are C infinity. Okay, and functions which are infinitely differentiable and satisfy the condition conditions. Okay. So you take any polynomial. So to start with monomial x to the alpha, and then you take the differentiation of phi of order mod beta. Okay, and then you take the supremum over all x in Rn. Okay, so these should be finite for all multi indices alpha beta. Okay, so just have a closer look at this definition. Okay, so we are multiplying any derivative of phi with a polynomial. So this polynomial and order of the differentiation are arbitrary. So they are all finite, but they are arbitrary. Okay, and for all these things, so then you multiply this derivative by the polynomial and take the supremum over x in Rn. That should be finite for all multi indices alpha beta. Okay, so a typical example. Okay, so since first look this condition looks very stringent, so we should have some idea about the existence of such functions. So typical example. Okay, so this appears again and again. So this is the typical Gaussian. Okay. Okay, so this and this S is a, so this I said only C infinity functions, so they can be either real valued or complex valued. Okay, so that we need not repeat that. So these functions can be real valued or complex valued. So it's very easy to verify that S is a linear space. So that's a vector space. Okay, so if you are used to this terminology, so if you take complex valued functions, then S is a complex vector space. Otherwise, it's a real vector space. Okay, so that's very easy to verify because the conditions are just so if you take two functions, okay, so phi and psi in C infinity functions, so then d beta of phi plus psi just separates and the absolute value makes it less than or equal to. So that's straightforward verification that it is a vector space. Okay. So now we are going to introduce a topology on that, but this topology is much simpler than the one we introduced on d omega. Okay, so that d is still here. Okay, so d of Rn. Okay, so we introduce these actually they are norms. Okay, so this once we introduce these norms, family of norms, on S. Okay, so phi of M is, let me write that. So sup over x in Rn, and I am taking summation over all multi indices up to order m, and this 1 plus x square to the, this is just a choice. Okay, so you can have different choices. Okay, so this is phi in yes. So we are not using all the derivatives, but we are only using the derivatives up to order m. Okay, so this is for m equal to 0, 1, 2, etc., all non-negative integers. Okay, so clearly we have this. So this is an increasing order. Okay, and this is a separating family of norms, separating family. What does that mean? So if phi psi belongs to the Schwartz space and phi is not equal to psi, then there exists some m non-negative such that phi minus psi m is strictly positive. Okay. So that enables us to define a metric topology on S, so that we stick to that topology in the study of the Schwartz space and its dual space. Okay. So a word about again the choice of these norms. So some authors use two indices. So here we have used only one. One for the degree of the polynomial and one for the order of the derivative. Okay. But even that the double sequence, they are all equivalent and define the same metric topology we are going to define. And also a word about this polynomial. So, this can be replaced by any other polynomial of course degree up to m. But again, of course the norms will be different, but the topology in the end, what we get, we may get a different metric, but as topology the topologies are same. Okay. So, this of course it happens in all d omega and even space of C infinity functions. Okay. This ambiguity is always there because you can choose in many ways, either the sequence of compact set and here sequence of norms or semi norms, but the end topology is the same, that is important. Okay. And okay, so this is topology on, let me just finish this topology on yes. Okay, so this is going to be a metric topology. In that way it is simpler compared to the topology on d omega or drn. Okay. So, if phi psi belongs to yes, define the distance. Okay, so this phi psi, this is equal to summation. Now, it will take all the derivatives of phi and psi. Okay, so this phi minus psi m 1 plus phi minus psi m equal to 0 to infinity. Okay. So, every term in this series is less than or equal to 1, but still it may not converge. So, it is a series of positive real numbers. So, you put a converging factor. Okay. So, we can again choose a different factor here, any convergent sequence. So, you can make that. So, this is less than or equal to 1 by 2 m. So, it is finite. Okay. In that way it is possible that we get many different metrics, but all these metrics give rise to the same topology. Okay. So, in this way whatever you, so even if you change the norms, okay, and then that changes the metric, but this finally the topology on S remain the same, and importantly that is what we are interested in, a convergence of sequences. Okay. So, that is important. Okay. So, just let me, so with respect to this metric, so let me just say about convergence. So, a sequence, so again by linearity, so it is sufficient to discuss convergence of a sequence converging to 0 in S, that is important, if and only if, because of that metric topology, this phi k m tends to 0 as k tends to infinity. So, let me write that. For m equal to 0, 1, 2, etc. Okay. So, that should happen. Okay. Equivalently, so you can just check that. So, this if you take again this polynomial and d beta, I will put it, okay, it does not matter, phi x converges to 0 uniformly, that is important, uniformly for all multi-indices alpha beta. Okay. And with this thing you can also check that, So, this is important for us, completeness. S is a complete metric space. So, it is a topological vector space where topology is given by a metric. Okay. And in that way it has rich dual. Okay. So, we have been talking of this dual all the time, why that dual has to be rich. Okay. So, the reason for that is we seek the solutions of our partial differential equations, especially linear ones, in the dual of such spaces, either in D prime or in S prime. S prime we are going to define that. Okay. So, that is the reason we are always looking for spaces having rich duals. Okay. So, here is an example. So, this is just where this dual can be nothing. Okay. So, dual consists of only 0 element. Okay. So, here is an example. Okay. So, you details you can work out. Okay. So, these are LP spaces, but now the range is 0 less than p less than 1, and consider this space and consider this space LP 0 1. So, these are measurable functions defined on the interval 0 1. Okay. So, here it is a norm, it is not a norm linear space. Okay. So, what we are going to, of course, it is a metric space, not a norm linear space. Okay. So, if f belongs to LP 0 1 in this range, by definition, okay, so this is the space of all measurable functions for which this is finite. So, unlike the case of p bigger than or equal to 1, so you cannot just put 1 by p and try to show that that is a norm, and that is not true also. Okay. So, however, this a metric space, however, can introduce a metric. A metric in LP. So, this is just d of f g f t minus j t power p dt. So, verify this is a metric. So, that is an easy exercise. This is a metric. So, LP becomes a metric linear space, and it can be shown. It's not very hard, but I'll just refer to Rudin's book for example. So this the dual space of LP 0 1 is just 0. Okay. So this any linear functional, continuous linear functional on LP 0 1 for this range, it is just 0. Okay. The main reason for this thing, okay, the reason for region, there are no non-zero proper open convex sets in LP 0 1. So that means if you assume that there is a open convex set, so either it has to be 0 or it has to be LP 0 1. Okay, those are the only two open convex sets. So that's why the locally convex topologies play an important role in assuring that the dual space is rich enough, and you also have Hahn-Banach theorem, closed graph theorem, all those things will come into play, though they are not nonlinear spaces. Just compare this example. So in for the range p bigger than or equal to 1, we have already seen that that's a nonlinear space. So and we know they are dual spaces. Okay, they are very rich. Okay. So coming back to again the discussion. So dual of S now, we'll talk about that. So dual of S. Okay, so this is, we denote it by as usual S prime, and this space has a name. This is called space of tempered distributions. So soon we will see that on this space tempered distributions we can extend the notion of Fourier transform. So that I will discuss in a minute. So as usual, this S prime consists of all linear continuous functionals, right. So this T from S into C or R, as the case may be. If you consider S as a complex vector space, then you take onto C, otherwise on R. Okay, that's our choice. Okay, so again continuity is with respect to the metric topology. So but here is an easy way of checking that. So this I state it as a theorem. Okay, this is, so I am just stating a simple version, but there is a stronger version of this theorem. So I am just confining only to one linear functional. So let T from S to C be linear. Then So, this is much similar to the case of a distribution. So, this you already seen it. So, T is in S prime if and only if there exists a constant C positive and an integer M also include 0 such that T of phi is less than or equal to C P M for all P in S. Okay. That way every tempered distribution, so every tempered distribution is of finite order. Okay. So, this is how you check whether a linear mapping from T from S to C is a tempered distribution or not. Okay. So, of course, M depends on T, and of course, the constant also depends on T. So, M may become larger and larger, but in any case for every T there is a finite M, that is important. So, okay. So, now several observations, comments, and a comparison between usual distribution and tempered distributions, etc. Okay. So, some observations. Okay. So, I will just for the sake of notation, so this space of test functions I denote it just by D and its dual just. So, this is just space of distributions. Okay. So, the first one, so this D consists of all C infinity functions with compact support, and whereas S consists only of C infinity functions with some properties. Okay. So, that so the sometimes the elements of S are called rapidly diminishing functions. And some authors use also decreasing. Okay. I write here diminishing. Okay. So, reason for that is, so if phi belongs to S, the Schwartz space, phi and all its derivatives tend to 0 as mod x tends to infinity faster than inverse of any polynomial. So, just look at the definition, you will see that. So, we will make use of this again and again. Note that the topology here is not a metric topology, whereas here it is a metric topology. So, the topologies are different, this D and S. Okay. Nevertheless, this inclusion is also continuous, meaning, so if phi k converges to phi in D, then phi k also converges to phi in S. Okay. So, this inclusion is continuous. So, again this is very easy to verify by using the definitions. Okay. So, we have seen that if f is in L1 log, then f is in a distribution. Okay. So, however, this is not the case with S prime. Okay. So, example here. So, you just n equal to 1. Okay. So, e to the x. This is a locally integrable function. So, this belongs to D prime, and with little work you can show e to the x does not belong to S prime. Okay. And same as for any n, you can use this one, e to the x square, again locally integrable function. So, you just, but again this is not in S prime. Okay. So, the way we associate a distribution to a locally integral function is via going integral, right. So, it's same way f phi. So, phi in D in this case or S. Okay. So, that is what we want to do. So, here you just work it out, but here it is very easy. So, if I take this e to the minus mod x square, that is in S. Okay. But if I multiply this e to the minus mod x square and e to the x square, and that becomes 1, which is not integrable. Okay. So, that integral is not defined. So, you see quickly this e to the mod x square is not in S prime. Okay. Whereas, so it is very easy to see that if f is in LP, p bigger than or equal to 1, then f defines a tempered distribution. Again via the integral. Okay. So, let me not write Tf. So, because we identify f with Tf. So, again I just define f of phi. So, this is just f of p. So, phi in S. So, we have to verify two things, that this is finite and then it is also continuous. So, continuity is straightforward, you use some dominated convergence theorem or things like that. So, only this finiteness. So, in order, since f is in LP, it suffices if I show that phi is in LQ, then that integral is finite. Okay. So, once we show that, that is fine. So, here is that thing. Okay. So, if phi belongs to S, then d alpha phi belongs to LP for any p infinity, okay, and all alpha, multi indices alpha. Okay. So, this is an important thing we use all the time. Okay. So, let me just do it for alpha equal to 0, that means just the function phi. So, we want to show that this phi of p when you integrate over Rn, that is finite. Okay. So, this we write it as, you do the same thing for other derivatives. So, I multiply this by this polynomial sum m minus m. Okay. And since phi is in Schwartz space, so this supremum if I take, so this is a bounded function for any m. For any m I can do that. Okay. So, that implies integral phi x p is less than or equal to some constant I write. So, that is the bound integral 1 plus mod x square to the minus m. So, this constant comes from this bound, and that is in the terms of those norms we have already defined. Okay. So, if I show that this I can choose an m such that this integral is finite, then I am done. Okay. So, that shows that phi is in LP, and similar arguments for any derivative. Okay. And this is an interesting integral. If you have not seen it earlier, you should do that. So, this is finite for m bigger than n by 2. So, in fact, this integral can be evaluated in terms of the Euler gamma function. If you have not done it, do it. It is a nice exercise. First you do it for n equal to 1, and then for generally n you use spherical coordinates. So, this is an interesting situation. So, all the functions in S, they are in LP space. See, the L infinity is already in the definition. So, they are all bounded. So, there is no problem. So, the integrability can be obtained in this way. And once we know that this phi is in any LP, so in particular we can use that in LQ, where Q is the conjugate of P, then we show that any LP function defines a tempered distribution. So, the finiteness is okay, linearity is okay. So, you have to only check the continuity. So, continuity either you can use Schwartz theorem, okay, so that I mentioned here. So, just bound like this, or you can directly use the definition of convergence and prove the continuity. Okay. So, I stop here and continue discussion on this Schwartz space, class of Schwartz space. Okay. Thank you.